Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. It's actually part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Connor Stone with us today. Hey, Connor.
Hello.
How are you?
I'm doing great. How are you?
Doing well on this September 26th, post-equinox. Although we are post-equinox, nobody has told Phoenix yet about that. So we're still rolling at 100 plus degrees. And you are in Montreal, yeah?
Yes.
Very cool. And is fall starting in Montreal?
A few eager trees are getting going, but still mostly green.
You eager ones. Very cool. Very cool. And what's your position there at Montreal?
So I'm a postdoctoral fellow at University de Montreal and at the Mila AI Institute.
Oh, very cool. And
So I
you
just
just
started this month,
very
so
good.
it's
So you
still kind
just
of
got your
chaotic.
PhD, so it's Dr. Stone. Congratulations,
I did, yeah.
Dr. Stone. That's very awesome. Where did you do your grad work at?
So I was at Queen's University,
Mm-hmm.
just down the road, really.
Yep. It wasn't like it was, another part of the world. Very cool. Very cool. And Connor, what do you like to do for research?
So I study galaxies, mostly galaxy observations, and I like to try and use like Bayesian statistics and machine learning and whatever I can to extract out information about the structure of these galaxies.
Very cool. Very cool. And that is going to bring us to this very awesome APJ supplement article. Probes. One, a compendium of deep rotation curves and matched multiband photometry. And Connor, take us away.
All right, so I think before I get started, I should really say that this has been a combined effort for about 5 years between myself, Stefan, Nick, Matt, and Tom. So all the co-authors listed there. This really got started with the very first bit of real research that I was doing in my master's study.
Okay.
And I was looking at this radial acceleration relation, trying to test different models of dark matter.
Yes.
And I needed a set of galaxies with rotation curves and photometry to analyze with. So that's where this got started. And since then,
Cool.
I've added more catalogs to it and built it up. And we've gone back and forth between the team, sort of testing this data. And what we've come up with at this point now, 5 years later, is something that is a whole bunch of data for galaxies with rotation curves, surface brightness profiles, and a lot of sort of tested structural parameters for these galaxies.
Nice. Nice. 3,000 leak type spirals. Wow.
Yeah, so 3,000 with rotation curves, and then about almost 1,700 that we have matched photometry for them in a whole bunch of different bands.
Nice. Okay. Very cool. Okay.
Yes. So we've sort of tried to compile as much useful information about these galaxies as possible. And you can see sort of in the introduction that we're listing the wavelength bands we've got from FUV, NUV, G, RZ, W1, W2. So we go all the way from UV to mid-infrared.
Yeah, very nice.
Okay. And we've also got a lot of other information about these galaxies. For example, in figure 1, we show the morphology for these galaxies. And looking at it, you can see that this is all late type galaxies, so spiral galaxies, and we've got a whole different range of morphologies. So whatever kind of galaxy it is that you want to study, there's something there for you. There's a there's a bit of a dominance in the like SB to SC type,
Sure.
but that's because a lot of the sub samples that we built up together, those really favored SB and SC type galaxies. But altogether, we do cover a pretty broad spectrum of morphologies. So that's really nice to have that coverage there. You're not really overly biased to just focusing on one type. You can
Mhm.
see, you can sort of track changes over the course of morphology.
Right. Very cool. Very cool.
Yeah.
And so this data is part of the article, right? This is something you download with the article?
Yes. So this is the data is included as supplementary data for
Got
the
it.
article. And what's included in there is rotation curves and surface brightness profiles. So you've got the raw data pretty much right from either the individual surveys, the 7 surveys that are listed there in the legend. Those are the different surveys that collected rotation curves. And
Mhm.
then what I did is I used a bunch of large surveys to collect matched photometry for them.
Yeah.
So that matched photometry is the actual stuff that I did really. The rotation curves I pretty much copied
Uh-huh.
uh, uh, from their original papers and brought them together in more of a uniform
Mhm.
format,
Yeah.
just to make it easier for people to use. So yeah, you can see here that we've listed each of the different samples. They all have different
Yeah.
parameters, like different selection criteria that they used to choose their galaxy.
Sure.
In general, it's all like redshift 0 galaxies, ones that are large enough on the sky that we can relatively easily resolve their structure. So like an arc minute, more
Okay.
or less.
Okay.
And so you can get, well, their morphology, but you can also get their resolved structure for a whole bunch of different wavelength bands, even W1, W2, which have a pretty large
Yeah.
PSF.
Wow.
As long as you're not really worried about the center, you can see what's going on with those galaxies. Um, so each one of the surveys has a different number of galaxies as well. Some of them are a little smaller. That Spark one has about 163 galaxies,
Yeah.
whereas some of the Mathewson ones earlier on had over 1,000. And
Yes.
um, so different numbers of galaxies for each one, but that's fine. Get it all together, get it in a uniform format. That's really
Right.
the idea.
Right. Right.
And make it easy for people to grab this data and do their own science with it.
Lovely.
Um, yeah. And along with that raw data, the rotation curves and the photometry, we've added a bunch of other things. You can see there's distances that we've got at section 2.3, where we more or less explain how we got those distances. We were using the cosmic flows calculator, which
Okay. Mhm.
lets us get distances at least for local galaxies, but that's fine because that's what we have.
Absolutely.
That's nice and easy. Um, then there's the rotation curves, which are mostly long slit H alpha,
Okay.
like along the major axis.
Mm-hmm.
But there are some H1 rotation curves. Those come from the Spark survey.
Okay.
So there's a bit of variety there, but for the most part, it's H alpha. That's where most of the data is coming from.
Okay.
And a lot of these surveys were actually done back in like the 90s or early 2000s.
Mm-hmm.
And so it wasn't quite as competitive for telescope time on some of the telescopes that they were using, and they were actually able to integrate for a fairly long time. You can see in
Okay.
figure 2 here that a lot of the rotation curves we have go out quite far. So
Ooh.
there's a bit going on this plot here, and so what we're trying to show is the radial extent of how far out our rotation curves go.
Right.
And we've got 3 different measures for that. The brown would be just in kiloparsecs, physical distances, how far out
Got it.
those rotation curves go.
Okay.
The purple and the blue are relative to some measure,
Sure.
R23.5 or RE.
Uh-huh. Uh-huh.
And for the R23.5 and RE, we can actually compare to uh, other surveys like Manga and Khalifa, which they have a limit out to how far they would go.
Mm-hmm.
And so you can see, like for the purple distribution, the purple dashed line shows you how far out Khalifa goes.
Mm.
And what we were trying to get across here is that these are really deep rotation curves, and so a lot of them actually extend out further than what you would get with other large surveys that give you lots of rotation curves.
Okay. Cool.
So if you're looking to do statistics with your galaxies and you want to get up in the 1,000 or higher range,
Mm-hmm.
then this probe sample actually gives you some deeper rotation curves than you're going to see in a lot of other
Nice.
comparable surveys. So
Nice.
that's one of the things that makes it kind of special.
Yeah, it's unique in that regard. Mm-hmm.
Yeah.
Very good. Very.
Let's see. So yeah, that gives you a sense of the radial extent, how far out these rotation curves go. I
Uh-huh.
should mention as well that a lot of the ones that don't go out very far, that are on the left edge there,
Yeah.
um, it's partly because they were in cluster environments, and they're actually like, it doesn't matter how long you integrate, you won't go out any further. That's just where the H alpha ends.
Yes. Yes.
um, so sometimes there's like a physical reason for why the
Cut
rotation
off.
curves don't go out so far.
Yeah. Yeah. Okay. Cool. All right.
So what you can see just on the section 2.5 there is the DESI Legacy
Mhm.
Imaging Survey Photometry. So DESI is great. It's almost like next iteration of SDSS. It's got even deeper photometry, and
Yeah.
it's got a really, like, what I liked about it while I was writing the paper is there's a pretty easy interface to pull data from the survey.
Good.
So I was able to download all of this really easily and process it with the autoproof code that I actually wrote for one of my earlier papers.
Cool.
And actually all four papers that I published during my PhD used this probes sample.
Mm-hmm.
And several other people in the group that I work with are also using this probes data. And now they finally have a paper to point to say like, this is the data that I've used.
Very good.
so
Very good.
so yeah, autoprof is what I used to process that
Okay.
data. I would look at the R band specifically to get my non-parametric isophotal photometry. And then
Okay.
I would use forced photometry to extract the same isophotes from the other bands.
Okay.
That way, when you want to look at color information for these galaxies, even if you want to do like a profile of color,
Okay.
all the pixel to pixel comparisons match up exactly. So you're not trying to measure a color on two different parts of a galaxy, because it matters that you get it pretty precise if you want to look at that.
Okay. Oh yeah. Uh-huh. Very
Um,
cool. Is
so
auto
yeah,
is auto prof is that public? People get that?
it is public. It's published at that Stone 2021B,
Okay.
and Autoprof. I wrote it to make the whole process of photometry like as pain-free as possible. You can, if you want, literally just give it a FITS file and a pixel scale, and it'll do the rest for you to
Nice.
get you a surface brightness profile.
Mm-hmm.
Um, and then there's a whole bunch of extra analysis routines you can tack on to get more information. For example, in the probes galaxies, I did radial wedges, which is essentially, instead of a surface brightness profile where you average around an elliptical isophote,
Mm-hmm.
you actually, starting from the center of the galaxy, I have four different rays that go
Oh,
along the different
okay.
major and there's semi-major, semi-minor axes,
Okay.
and they go along that direction and give you a surface brightness profile just for that like quadrant of the galaxy.
Got it.
So there's a lot of structure information that you can get in there, especially because these are late type spiral galaxies. There's a lot going on with those galaxies, more so than just an ellipse.
Yeah.
And that information is all there in the probes samples already processed for you.
Nice.
So that's nice. I don't know if I'm going over time. I can keep talking
Oh
about
no,
this
keep
forever,
going.
but
Wait, APJ supplement, go.
yeah. So then section 2.6, the unwise photometry. So that's us trying to push into the infrared. You get a lot of good information about the stellar populations in those galaxies, so you can get good stellar masses that way. Um, the resolution is not as good for W1, W2 as it was for our DESI imaging. We still use forced photometry from that R band,
Okay.
keeping everything consistent in a sense, but the different resolutions mean that towards the center of the galaxy, um, you're probably not going to see a good matchup between the two different bands. But once you get out a little bit, then everything starts to line up and you get really, really good results that way. So that's why we kept the forced photometry from the R band into here.
Makes sense. Okay.
And I guess to finish off the photometry, we can scroll a little further to the Galax photometry. And that gives us UV, which I actually haven't done too much with UV before, but I know that it's like useful to have as much wavelength coverage as you can if you want to try and do SED fitting for galaxies and get a little more information about the stellar populations in that galaxy.
Right.
So I calculated stellar masses for all of the galaxies in the probe sample, but I was using like color mass to light transformations. If someone wants to go ahead and do some SED fitting, they are welcome to do so, and this should help them along with that process.
Absolutely. Very good.
Yeah. So that's sort of the core data that is in this probe sample, and a lot of the things that I've calculated beyond this are really just to help people out to use this sample to the best, like to make it as easy as possible to really quickly get your science done with this. Awesome. So the figure 3, just up a little bit. This I was trying to get across some of the scope of what you can do when you have a large sample here. So what I've done is I've broken down all of the galaxies by their concentration on the vertical, like the different rows. And for the different columns, I broke them up by different stellar masses. And
okay.
And you can see that there's enough galaxies in every bin that I can actually start to get some average structure for these galaxies. And you can see in the upper right, where they're very concentrated and very massive, the inner part of the rotation curve jumps up and then it's quite flat.
Right.
Whereas if you go down to the lower left, then the rotation curves take a long time to rise up. So there's structure that you're starting to see because you have enough galaxies in this sample that you can break it down by a couple parameters and still average out to see what's going on here and not worry so much about the noise.
What a
so yeah, that's kind of a fun thing that you can do when you get a larger sample together, and you can start to see some structure breakdown in the different rotation curves and in the data.
Yeah, and when it's on sort of a equal footing, right? Because you took many of these sources and sort of somewhat homogenized them in terms of
exactly. And so this doesn't take too long to put together. Now that I've done all the work of getting all of these different surveys together, which each one, of course, had its own format to begin with.
Its own idiosyncrasies, yep.
And so wrestling it all into a sample where you can start to ask it questions like this, like what are the structures of these rotation curves? That was one of the main thrusts of the paper, and the thing that I've been doing for the last 5 years in order to get this ready to go.
Yes.
It's been at various stages of readiness over those 5 years, because of course I used it in all 4 of my papers, but I now have it in a stage where I can give it out to other people.
Right.
Yeah.
Right. Very cool. Very cool. All right.
So if we carry on down to the next figure, I wanted to, this is a data paper, so I want to let people actually see some of the data as it is.
Yeah.
So here's some rotation curves where we're stepping in mass bins all the way along. At the top, we have a very, very massive galaxy, and you can see that there's a lot of data for that galaxy.
Wow.
And you can start to see that there's structures in there that are larger than the errors. So there's something going on in those rotation curves then that is more than just the smooth models that I fit. You can see for each one of the rotation curves, I fit this C97 model and a tan H model. Tan H is sort of your simple like rise and then flat rotation curve.
Right.
C97 allows you to explore a little bit more if there's any sort of tail off or rising rotation curve towards the end, or if there's peaks at the, well, a single peak near the center of the rotation curve. And so you get a little more structure about that rotation curve, and you can start to study like how common are rising or falling rotation curves. Yeah, so now when you get way down to the bottom, you're starting to look at we have a few even dwarf galaxies in the sample, and dwarf galaxies are complicated things to look at.
Well, yeah, relative to these big heavy ones, sure.
Yeah. So there's a bit more exciting stuff maybe going on in the dwarf galaxies, but also complicated stuff. There's clearly a lot going on in that NGC 4294 that is not covered by the smooth models,
right?
But still the global structure is covered by that.
Follows along, absolutely. Deviations around the mean.
Yeah. So what's a nice thing about the probe sample is that it goes from dwarf all the way up to very massive galaxies. So you get the context all the way along. If you try and just study dwarf galaxies, you may not see how it changes as you move into the more massive regime. So that's a nice thing that we've got. And actually, one of the co-authors on this paper, Matt Frost, he's working on an extension to probes, a probes 2 that will add more and more dwarf galaxies, so we can really flesh out that lower mass end.
Okay.
So that'll be an exciting thing coming in the future. I don't know when it'll be ready though. Hopefully not 5 years again.
Yeah, probably more like a year.
Yeah, well, now we've got the format and everything down, so it's not so bad.
Yeah, it'll be a lot easier to augment the catalog.
Yeah. You can see their equation 2. We've got all of our rotation curves have a more uniform format, and one of the things that we did is we subtracted off the systematic velocity for all the rotation curves. So you can see over on the figure that everything is going around 0.
Yes.
And that's how the data is presented, because for some of our galaxies, we actually have multiple rotation curves. And depending on the calibration that was done that night, the like systematic velocity can change a little bit. So we just zeroed that out, made it easy to use. And then
got it.
The velocities that we're showing like in the figure and that we use later on for our structural parameters, they're corrected for the inclination of the galaxy and the redshift.
Okay.
The redshift correction is very small. These are all near redshift 0 galaxies, but we still include it anyway. Okay. And the inclination correction, we have a global inclination that we've calculated for every galaxy.
Okay.
And we calculated that inclination from our R-band data. Yes. So that's the photometry sort of helps us understand our rotation curves a little more. And so we can correct all of that. And if someone wants to do something else with their rotation curves, they certainly can, because the rotation curves as stored in the data files, they just have the systematic velocity subtracted. The inclination and the redshift corrections aren't in there because different authors may have different ways that they want to apply corrections. So we tried to keep it as raw as possible in there.
As possible.
Yeah, but all the structural parameters, we've picked our set of corrections and gone ahead with those. And so anyone who doesn't care too much about that can still use reasonable values that are in those data tables.
Okay, got it. Very cool.
Now, so that's a lot about the rotation curves, and then the photometry, which we're getting to now. The photometry has its own set of problems to work with. For example, the truncating the surface brightness profiles with non-parametric isophotes. Essentially, what we're doing is putting rings on the sky, calculating the average brightness in that ring, which means that your brightness drops, and then at some point you kind of just hit noise.
Okay.
And we have to figure out where that transition is.
Right.
And we don't want to be too conservative because then we lose data, and we don't want to be too aggressive because then we're just adding in sky and it adds noise to everything.
Right.
So if you go to the figure, I think 6.
Ooh, there we go.
Yeah, figure 6. So this is our procedure that we ended up with after trying out a whole bunch of different things. Essentially, we removed the first couple magnitudes up at the top, and then we try and fit an exponential to the outer parts of the surface brightness profile, and we fit an exponential to the sort of the rest of the profile, the flat area, which isn't always perfectly flat, but it's usually pretty close. And with those two, we can get the intersection point to figure out where the region where the end of the rotation, the surface brightness profile is.
Okay. I'm following.
So
I'm with you.
So we do that for every one of the surface brightness profiles, and that truncation point is stored in the data files. So you can just load that in and use it. You don't have to recreate this whole analysis in order to get nice, clean surface brightness profiles out of the data. But the whole raw data is included. So if you want to do your own thing, you're welcome to do so. But this is what we did for ours. And once we found the truncation point in the R band, we used that for all the other bands. And we tried doing it band by band or just R band. Turned out that R band was reliable enough that was the better way to go for the rest of the large sample. And figure 7 actually shows you for this galaxy what it looks like when you look at all the other data. So you got 7 wavelength bands. The 3 blue ones are the GRZ, the DESI photometry. The brown and black one, those are the infrared bands, and then the purple ones, those are the UV data.
Interesting.
Yeah, and interesting thing about the UV data that I didn't know going in, but I've since learned, is that the center of a galaxy is sometimes a little depressed in brightness. You can see that in the far UV band. It sort of starts low, goes up, and then comes down.
Yeah.
So I learned a whole bunch putting this paper together. That was one of them.
Good. Everyone else will too.
Yeah.
Very good.
You can see the error bars on these as well. We've actually multiplied them by 2 so that you can see them.
Okay.
And even still for the DESI data, you don't get to see much errors because statistically there's almost no error. Like the random errors on these are super small. It's really more the systematic error that is what comes into play, and that isn't included in the surface brightness profiles themselves.
Okay.
But you can see actually if you go up to figure 5, the one before this, that we sort of wanted to give a picture of what the errors look like in our data. So this is the whole probe sample, every band. The x-axis is the surface brightness, and then the y-axis would be the random error on that data point.
Okay.
And so what you can see is for each band, there's essentially everything above a certain brightness is fine and easy to measure, and then it explodes when you get to essentially the limit of what that detector configuration could do.
Yeah. Yeah.
Um,
Wow. Okay.
so you can see differences between like the UV data, the DESI data, and the WISE data in terms of their profiles. And that's just because they had different observing campaigns, different instruments, different integration times,
Right.
but still,
But there's some
lots.
similarity between them too.
Yeah, they all have the basic structure of like shooting up at some point.
Right.
Um, so what you can notice for quite a lot of them is we go all the way down to 30 megs per second squared
Cool.
in some of our surface brightness profiles.
Mm-hmm.
One of the things that the autoprof code does
Wow.
is it uses a band of pixels instead of just a single line of pixels for the isophotes at the outskirts of galaxy,
Okay.
which means we can actually get about 2 or 3 magnitudes deeper than a lot of other surface brightness codes.
Mm-hmm.
So that shows up here in some of the surface brightness profiles going deeper than other catalogs would, even with the same data.
Yeah. Mm-hmm. Nice.
So that's a nice feature that we have for our photometry is really quite deep. Anyone who's looking at kinematics and photometry for galaxies, this is probably the best sample they're going to find in terms of the depth of the photometry that matches with it.
Yeah, that's going to help the science cases that people will apply to these. Mm-hmm.
Exactly.
Very cool.
So that gives a sense of the photometry that we've
Mm-hmm.
got for all
Beautiful.
of these galaxies.
Beautiful.
Again, this is a data paper, so we're just trying to convey like what is it that you're getting when you download all of this data.
What's in the
And
box?
what's in the box. Yeah. So some of these figures people might have produced on their own, but now I've just done it for them, and they can just use that.
Move on to the.
um, we've also got a lot of photometric corrections. Yeah, you can see
Mm-hmm.
that in
Mm-hmm. Yeah.
equation 3. So we've got the galactic extinction, we've got K correction and cosmological dimming all already available for all of the galaxies.
Very nice.
And um, so these are fairly standard, and the K correction and the cosmological dimming factor, those are both pretty small for most of the galaxies because it's all redshift 0. It's all very close to us.
Right. Mm-hmm.
Um,
Mm-hmm.
but for the WISE data, actually, the K corrections aren't that small. They're still noticeable. So it was important that we included it,
Yeah.
but it doesn't make a huge difference.
Yeah.
um,
Good. Mm-hmm.
and one of the things that does come in to play though is in the next figure. When you're doing photometry, it matters how inclined the galaxy is as to how much dust you're looking through, and
Mm-hmm.
and basically, if you want to measure a radius for a galaxy and the galaxy is inclined, it'll actually um, change the brightness of everything. And so you're not looking at the same part of the galaxy depending on how inclined the galaxy is. You can
Mm-hmm.
imagine if you're trying to get, say, the R 23.5 for a galaxy, and then you incline it and everything gets brighter, that R 23.5 moves in towards the center of that galaxy. And
Yes.
that's not what you want. So here we've applied a correction
Okay.
for the inclination
Mm-hmm.
of these galaxies.
Mm-hmm.
And that correction, you can see, depends very much on the band that you're looking at. The way that we did it was
Yeah.
by looking at a color. So
Huh?
relative to the W1 colors, which W1
Okay.
can
Yeah.
go through the dust for the most part. It's not very affected.
I got it. Mm-hmm.
And so if your color changes relative to W1 as a function of your inclination, then that means you're being affected by the inclination
Mm-hmm.
um, in some sort of significant way. And the UV data is the most impacted, as would be expected.
Right.
G and R do have a noticeable effect from the inclination, but then once you get up into the infrared, so the Z band and the W2 band, they can see through the dust for the most part, and essentially the galaxies are transparent from their perspective. The inclination doesn't matter as much. So then
Certainly.
I was quite happy when I made these plots and those corrections came out to zero. I was like, yay, the science actually makes sense.
Yay. Yeah, the trend is not very nice. Got a good explanation. Cool.
So there may still be structural inclination dependence, because if you imagine a galaxy as just a slab, when you tilt it, you are still looking through a thicker part of the slab. In principle, if you tilt it to 90 degrees, you're looking through an infinite slab, and your brightness should be infinite. But that's not what we actually see. The brightness of the galaxy doesn't go to infinity. So if someone wants to apply a structural correction, they can do that. But the dust correction as a function of inclination is already handled for them, more or less.
Cool. To some degree. Very cool.
And these corrections are applied directly to the surface brightness profile before we calculate our structural parameters. It's not applied to the surface brightness profile as recorded in the data tables, because again, we're trying to give people as raw data as possible, so they don't. So we're not doing some weird correction that they have to try and undo later. The data tables are pretty much right off the telescope, but the structural parameters that we calculate later, they've included all of these corrections that I've talked about so far.
Okay. And
so now that we've sort of wrangled our photometry to get it into some sort of meaningful values, then we can start to get the structural parameters. And you can see, so section 3.2.1, that's our radii. We have a whole bunch of different radii, so isofocal radii, effective radii, stellar mass radii. So that would be probably figure 10, I suspect. And we've sort of plotted out for one surface brightness profile where all of the different radii land. So yeah, there's the isofocal radii, those are the light blue ones, and those go from 22 to 26. Percentage radii, so 50 would be the effective radius, but sometimes, like if you want to look at concentration, you would use the 20% and 80%. And so we just throw everything in there and let people choose their poison. We've got
very good.
Got stellar density radii, so stellar mass per parsec squared listed there. And also listed is the last point of the rotation curve. So yeah, exactly. So that's how far the rotation curve goes out for this particular galaxy. And all of these are listed for every galaxy. In fact, because we have so many radii and we calculate all of our structural parameters at each one of those radii, the table of structural parameters has like over 1,500 columns.
Wow.
So there's a lot of stuff, a lot of information in there that we haven't even fully explored yet. But that's why we're releasing it to everyone.
Well, you're enabling other people's science, so that's fantastic.
And the figure before this one, figure 9, is sort of an example of so this is an example of the kinds of parameters that you're getting for every galaxy. There's the radius up at the top, which I just showed. We've got a whole bunch of different metrics for what our radius is. I picked one for the sake of the figure. And then there's the luminosity, the velocity, like the rotation velocity, the color of the galaxy, concentration, the
Surface.
stellar mass density,
Mm-hmm.
uh, the integrated stellar mass, and because we have rotation curves, we can get the integrated total mass within a radius.
Nice.
So all of these are calculated at all of those listed radii, and a lot of any ones that are band dependent, we've also calculated them for every band. So there's
Wow.
a lot of
Wow.
there's a lot of structure that you can see in this, like, I don't know what is it? It's 8-dimensional parameter space that we've got here. I like to do machine learning, so I like to look at high dimensional parameter spaces when I can.
Right.
Um, and so there's a lot of classical, like, scaling relations that are pretty much straight lines over the course of several orders of magnitude. But there are some others, anything connected with like the concentration or the stellar mass density, you start to see some like curvature and structure coming out here.
Yeah. Uh-huh.
That's the kind of stuff that can get me excited about some data. Is something nonlinear that I can
Yeah.
use machine learning on.
Mhm. Uh-huh. Exactly. Very nice. Wow.
So
It's a lot of
it's
data.
fun to look at this. It's really useful for, say, putting a result in context, like any sort of simulation paper. They may only have a handful of galaxies, and they want to try and present them in a context of like, is this a weird galaxy? Is this matching up with normal galaxies? You can just throw this data up on the screen, get
Right.
some contours, and you can tell the context of where your galaxy lands in just about any parameter space because it's all pre-calculated for you.
Wow. Mm-hmm. That's awesome.
So that's quite nice.
Very
and
awesome.
and yes, that's why our team, my supervisor, my PhD supervisor, Stefan Corteau, the second author on the paper, his team has been using this data a lot, even when it's a simulator in the team. They use this just as a reference point for context.
Cool. Yep. Very cool. Go Stefan.
Yeah. So if we scroll along, there, equation 6 and 7, those are the models that we have for our rotation curves.
Uh,
6 is just a tan H,
uh-huh.
and 7 is this it's the Cortot 97 model. It's actually from Stefan, one of Stefan's papers.
Mm-hmm.
And the parameters themselves, the beta and the gamma,
Yep.
don't so much have um, a clear meaning in units, but basically beta controls uh,
Slope.
the slope of the outer rotation curve,
Uh-huh. Yeah.
and gamma tells you how quickly the transition happens between the rising and the flat part of the rotation curve.
Okay. Mm-hmm.
That's what the physical meaning, more or less, of those parameters is. But you kind of have to play with them to really see what they do. And if you don't care, then you can just take the parameters which are listed in the data tables
Okay.
and throw them into the equation, and now you can sample your rotation curve at any point that you want. Um, just makes life easier.
It does. Mm-hmm. Yes. Yeah.
um, so if we scroll down a bit further, we've already looked at the uh, figure 10.
Yeah. Mm-hmm.
Those other equations are really just spelling out how these
The
different parameters are calculated. So
right.
concentration is R80 over R20, and
Mm-hmm.
um, then there's Cersic fitting. So I use non-parametric photometry.
Okay.
Uh,
Why?
a lot of people like to use Cersic photometry. So what I've done is I've fit a Cersic profile to our surface brightness profiles, and that can give you information about the uh, like, some people use Cersic parameter as a concentration parameter,
Uh-huh.
and so you can totally do that. That's already there for you in the data tables, already calculated. Um, looking at the next figure here.
Oh yeah. Velocity.
So
Yeah.
um,
All right.
now that we did these rotation curve fits with the C97 model,
Okay.
we want to look at how explanatory is that model, like how much of the data
Yeah.
does it represent?
Mm-hmm.
And what you see here are the velocity residuals from the C97 model for every rotation curve that
Wow.
we've got.
Okay. Mm-hmm.
And the top one gives it to you just in kilometers per second units, which is easy to think about. But I actually prefer the bottom panel, which does it relative to the error on that data point.
Okay. Mm-hmm.
So
Mm-hmm.
it's residual over error.
Yes.
And what you can see is that the residual over error is more than one, which means
Yeah.
that which means that there is information that isn't just random errors in these rotation curves, which means that there's structure in these rotation curves more than the C97 smooth model is representing.
Okay.
And that's probably non-circular motions and other sorts of interesting features that happen in rotation curves because galaxies aren't boring, infinitely thin disks. They've got stuff happening.
Got stuff happening.
Yeah. So that actually comes out of the data here, and you can
Yeah,
see
cool.
you can see that there has to be more going on. And also you can see that it gets narrower as you go further out,
Yes, on both.
which means that there are less of these factors happening as you go further out in the galaxy into the disk, which
Right.
makes sense because a lot of non-circular motions are happening near the center of the galaxy. If, for example, you have a bar, that's really a major feature, but at the center of your galaxy, not in the outskirts.
Yep. Yep. Very cool.
So I was happy to see that sort of comes out of the data.
Yeah. Makes sense. Totally. Okay.
And I think at this point we're getting down to the last figure, because all of these equations are really just spelling out how the parameter is calculated.
And what's in the columns and so on. So the data tables. I think we got one more. So
the data tables themselves are CSVs, so those are fairly straightforward. This table here shows you the layout of what our surface brightness profiles give you. This is also explained in the README file along with the surface brightness profiles. So
metadata.
Not too tricky there. But there's more than just the surface brightness profile. By having the ellipticities and the position angles, you essentially get a structure profile for that galaxy as well. You get more information than just the light. You also can see there may be twisting of the isophotes, which can happen along like spiral arms and stuff. So you can start to pick out features in these galaxies.
Nice.
And then that last figure, figure 12, is sort of
stepping,
just showing everyone what the kinds of SEDs look like. We've got 7 different wavelength bands, so you've got a large wavelength coverage, and you can actually start to see subtle differences between them. Some of them not so subtle. And so these are really ripe for SED fitting, and
it's just an example of what one can do with this.
Yeah, exactly. So sort of suggesting to the community, hey, if you want to do this, go ahead.
Go for it. Very good. Awesome. That's so cool. And I imagine you might be doing some of this or something about it, but we'll get to that in a second.
Yeah.
Very cool. Okay. We have a lovely data set out there. Connor, thank you so much for walking us through your very lovely supplement article.
Thank you for having me.
Sure. And you touched on it a little bit as you went through, but let me just ask a little more directly. So, let me ask it this way, where do we go over the next, let's say, 2 to 5 years or over one postdoc period on this project? You mentioned the possibility of a probes 2 at some point going on. I could also imagine doing some science, as you were suggesting there at the end, doing SED fitting and other things. And so where do you think this goes over the next couple of years?
Yeah, so as you said, probes 2 is sort of the immediate next thing that we're working on for that. So we're going to fill out the lower mass end, and a lot of exciting work is being done in the lower mass end. So that's one thing that we need to flesh out for probes. And I'm also working on the next version of AutoProf, which will allow us to sort of expand the sample more rapidly and also to further galaxies. So what we would want to do with probes is sort of keep building on it and build out more redshift so we can look at more redshift extensions so that we can look at evolution with time and stuff like that.
Yeah, nice.
So there's some exciting more directions that we want to go to build out this sample, and then the kinds of science that I want to do with it. I actually, one of the papers in my PhD, I looked at the scatter around scaling relations.
Okay.
And I used a Bayesian technique to get the intrinsic scatter, not just the observed scatter that has a whole bunch of error in it.
Sure. Uh-huh.
And so that intrinsic scatter tells you about sort of the history that those galaxies have gone through, because if they have stochastic star formation, if they have mergers, which of course the galaxies do, that can sort of puff out where the scatter is. And so the probe sample is what I would be using to sort of do that analysis. Actually, it is what I used.
Yeah, I was going to
say in my PhD. And as we build out the sample, then I can do studies of the scatter, but as a function of other parameters. So I can look at it in terms of environment. I can look at it in terms of evolution with time, and I can look at it over the course of the different mass regimes for the galaxies.
Sure.
So it's quite likely that like dwarf galaxies have more scatter than higher mass galaxies. But are we seeing that because there's more errors for these low mass galaxies, or are we seeing that because it's actually a feature? That's the kind of thing that I can study now when the sample is big enough that I can break it down.
Nice. Very cool. Very cool. Well, I really look forward to seeing some of that extra science and the expansion of the probes catalog over the next couple of years. It'll be really awesome to see.
Thank you.
Awesome. And that will do, Connor. Thank you once again. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.